Hello everyone, I'm Dr. Fawzul Atiq. I'm giving some series of lectures on the course Probability and Statistics. In the previous lecture, we have defined what is probability, the axioms of probability, few properties of probabilities, and couple of examples. In this lecture, we are going to discuss the probability of equally likely outcome. So here, that all outcomes will be equally likely. Just for example, suppose I throw a dice, and we all know that it has 6 faces. If the dice is equally shaped, so there will be no biasness in any of the face. If I have such case, then any face can appear with the same probability, right? Because number 1 can also appear with the probability. The same probability will happen for that number 5 will appear. So all the faces can appear anytime. We don't know, but all of them will have the equal opportunity. So these kind of outcomes, we call them as equally likely outcome, right? So in many experiments, it is natural to assume that all outcomes, it is natural to assume that all outcomes in the sample space are equally likely to occur. That is, consider an experiment whose sample space is a finite set such that S equal to 1, 2, 3 up to n. So that means basically S is equal to union of these singleton sets, right? And it has n number of outcomes. And because they are singleton sets and they are the different outcome of the sets of the sample space, so they are mutually exclusive, these sets. Therefore, I can certainly have and because all of them are equally likely as well, so their probability is also same. P of 1 equal to P of 2 equal to the event P of n. Now by axioms of probability, we can have that, as I said, that P of S equal to, and because this S set is union of this singleton set, so this is the P of this set 1 union set 2 union dot union that set n. Then by axiom 3, I can have probability of S is their individual sum. So therefore, this is P of 1 plus P of 2 dot up to P of n. Now I said that each of them are equally likely, so therefore their probabilities are same. Let us assume that each of the outcomes have probability small p. So each of them are individually p. Then if I take their sum, how many total numbers you have? Capital N number of, and each of them are individually p. So what is this sum value? It is capital N into small p. And therefore I can write that small p is equal to P of S divided by capital N. But what is P of S? It is the probability of the sample space. So by axiom 2, we have this is 1 and this is divided by capital M. So therefore I get that small p equal to 1 by capital M. So therefore I got this is equal to 1 by capital M. So each of the event, it is 1 by capital M. Now I can go back to that if I throw a dice, what will happen? That phase 1 will appear. It is the 1 by total number of outcomes, which is 1 by capital 1 by 6. In this case, capital N equal to 6, so 1 by 6. So that they have the probability 1 by 6. So this way, we can define the one of the outcome and its probability. So it is 1 by n. Now, probability of equally likely outcomes are there, and in this case, what will be the probability of some event? We have a theorem: if an experiment can result in any one of the n different equally likely outcomes, so that means the sample space contain capital N number of different equally likely outcomes, and if n of these outcomes together constitute the event A, that means A has small n number of outcomes, whereas they are all of them are equally likely, so but A has small n number of outcomes, then the probability of the event A is P of A equal to small n divided by capital A. So this we can prove it very easily. Now this is one kind of probability formula we all have learned in our like childhood. So how to prove that? So suppose A is equal to that all the outcomes we have, right? So we can write down all the outcomes. Yeah, just a second. I'm going to write down this. Yeah, suppose A is equal to the set maybe O1, O2. So all these equally likely outcomes. And A is a set which contain n number of which constitute of n number of events. So it is O1, O2, and I'm writing O small n. So that does not matter because each of them are equally likely events. So I have taken n pairs of this. So this order also does not matter. So I have just taken them. And it is already discussed that they are different and all of them contain one event. So they are mutually exclusive as well. Now I have probability of A is equal to P of the event O1 plus probability of the event O2 plus probability of the event ON. Why? Because A is the union of all these events, and then by axiom 3 we have the probability of a union is their individual sum. Therefore I can write down this. Now in the previous slide we have discussed that probability of each of the outcome is what? It is that 1 divided by the total number of outcomes. So P of each OI is equal to 1 by capital N for all I equal to 1 to up to capital N. So therefore these all the values are also 1 by n plus 1 by n like this. But how many such numbers I have? Small n number of. So therefore this value is equal to small n divided by capital N. Right? So therefore we can say that probability of the event A is equal to small n divided by capital N. That means number of favorable cases in A divided by total number of outcomes. Correct? I hope you understand. So this is what we have discussed. This is the whole theorem in a very formal way it is written. You can take a snap of it. I want to discuss some example related to this. Now look at this problem. Just make the video pause, understand the theorem question, try to answer it by your own. If two dice are rolled, what is the probability that the sum of the upturned faces are equal to 7? So how to do it? So you try to get what is the total number of outcomes, how many different ways that upturned faces will appear for the two dice, and after that what is the number of favorable cases that sum of the upturned faces will equal to 7. Yes, so total number of case is equal to, like, I have two dice. So for the first dice I have 6 faces, and for each of the 6 I have the second dice can also have the 6 number of ways. So therefore all total there are 36 different ways they both the dice may appear by the basic principle of counting, I can say. Now you find out the cases where the sum of the upturned faces will equal to 7. What are these cases? So it is the case that maybe first one will appear 1, second one is 6. First one is 2, second one is 5. Like that I can have 3 or 4. Then 4 or 3. First one is 4, second one appears 3. All these cases are, it is 7, the sum is. Then it is 5, it is 2. It is 6, it is 1. Do you have any other case? No? So therefore, how many such cases are there? There are 6 number of possible cases. Then what is the desired probability? So the desired probability is equal to 6 divided by, so small n is 6 divided by capital N, which is 36. It is equal to 1 by 6. Very easy. Without wasting time, let us move to the next example. But this is the solution, that is very formal way it is written. If you want to write down the whole thing, you can just write. Move to the next example. If 3 balls are randomly drawn from a bowl containing 6 white and 5 black balls, what is the probability that one of the ball is white and the other two is black? Again, make the video pause, try to think the answer of it. What is the total number of ways you have, and what is the total number of favorable cases of the event that you want to get the probability? See, 3 balls are randomly drawn from a bowl containing 6 white and 5 black balls. So try to find that how many total number of balls are there in the bowl. Yes, there are altogether 6 plus 5, 11 number of balls. And you are selecting 3 among them. How many ways you can do? So therefore, in this case, cardinality of the sample space will be, so it is a 3 number of balls you are going to select from 11 number of balls. How many ways you can do? It is 11 C 3 ways. All possible combinations, right? We have learned these things in our combination lecture. Now you get the number of favorable cases of this event, that one of the ball is white and the other two are black. Now see, you have total 6 number of white ball and you have 5 number of black balls. So among these 6 white ball, you have to choose one ball, and among these 5 number of black ball, you have to choose 2 black ball. How many way you can do? Again, so one ball you can select in 6 C1 ways, and for each of this selection you have 5 number of balls. From that you have to select 2 black ball. How many ways you can do? 5C2. So by basic principle of counting, it is their product. 6C1 into 5C2 ways you can have this selection. So therefore, what is the desired probability? Therefore, desired probability is 6C1 into 5C2 divided by 11C3. And if you just simplify this, you'll be getting it is 4 by 11. I hope you understand. So this example needs that basic principle of counting, probability of equally likely events, combinations, right? So that's the reason that if you just directly see this example, you may not understand. So you have to go through from the beginning. Okay. So the formal solution is this one. It has all the things are written in very detail. I want to show you a similar kind of example. A committee of 5 is to be selected from a group of 6 men and 9 women. If the selection is made randomly, what is the probability that the committee consists of 3 men and 2 women? See, this is the same concept as the previous example. So just make the video pause and get the answer. I hope I don't have to explain much. So the solution for this will be total there are 6 plus 9, 15 number of humans, and you have to select 5 among them. How many ways you can do? So 15 C5 ways. And how many ways you can choose the total number of 3 men and 2 women? So there are 6 men, you have to choose 3 men, and 9 women, you have to choose 2 women. So how many different way you can do? 6C2, 6C3 into 9c2. So what is the desired probability? Is equal to 6c3 into 9c2 divided by 15c5. So whatever I discuss, that is given here, the formal definition. And the final answer will be 240 divided by 1001, 1001. Now I have another good example. Read this example. An urn contains n ball, one of which is a special one. If k of these balls are withdrawn one at a time, with each selection being equally likely to be any of the balls that remain at the time, what is the probability that the special ball is chosen? Very interesting problem. Think of this example. So you have basically a n number of balls in a ball, and you are selecting k number of balls among them. You are selecting k number of balls among them. And in this n number of balls, there is a special ball, this one. Now in this k number of selection, this special ball may be there or may not be there. Anything is possible. The question is, what is the probability that the special ball is chosen? How to do that? Make the video pause, think of the question, try to answer it in your notebook or in the comment box. Then you see my answer. Yes, first you tell me that how many ways you can select k number of balls from a set of n number of balls from the urn. Yes, it is definitely nck ways you can select. So this is the total number of outcomes. That means the cardinality of the sample space. So capital N value. Now, what is that case that the number of cases you can have where this special ball is already selected? How many such way it is possible? See, if you consider the case where the special ball is already selected, then how many balls are remaining in the urn? N minus 1 number of ball, right? So there will be, because already the special ball is selected, so there are n minus 1 number of balls are there in the, and among this k also this special ball is selected. So how many balls are remaining in this each of our selection? It is k minus 1 number of balls. So how many total number of possibility it is? The same way I can say that is n minus 1 c k minus 1 ways. So this is the number of cases where the special ball is already selected. Then what is the desired probability? So the desired probability will be small p equal to that n minus 1 ck minus 1 the whole divided by n ck. And if you just simplify it, you will get it is k by n. Just simplify it. You know the factorial formula. This value is basically n minus 1 factorial divided by k minus 1 factorial into n minus k factorial. And this value is n factorial divided by k factorial into n minus k factorial. All factorial will be cancelled out. Finally, we'll be getting this is the value k by n. I hope you understand. Okay. Now, this is what we have already discussed. This is the solution for this question. The final value is, if I just simplify this value, I'll be getting k minus n, k by n. Now, this is very, very interesting problem. It is like you have to think a little bit to solve this problem. So first you try to understand what is the question. A 5-card poker hand dealt from a deck of 52 playing cards is said to be a full house if it consists of 3 of a kind and a pair. That is, three of the cards are of equal face value and the other two are also equal face value. Find the probability of being dealt a full house. So basically, you have a standard deck of 52 cards. From there, you have to select 5 cards, and a set of 5 cards is said to be a full house if you have 3 of them have the equal face value and the other 2 will have the equal face value. So suppose a full house, one of the example of a full house is 3 of a card. So maybe it is, first you understand that how many different type of card you have and how many different suites of card you have. We have 4 different suites of card, right? Heart, spade, and then what are the other two? Diamond and the other one. So we have 4 different suites of cards, and each suite is having 13 different number of different face value of card, right? So it is S, then 2, 3, up to 10, then J, Q, and K. So there are 13 different type of card we have, and we have 4 different suites. Suite 1, suite 2, suite 3, and suite 4. So they are club, heart, diamond, and spade. Now, a full house example is, maybe you got this face value is 3. So this 3 of maybe spade, 3 of diamond, and 3 of heart. So spade, diamond, and heart. This 3 you got it. And 2 of are the same face value. So other 2, maybe it is J of diamond and J of maybe the heart. So this is one of the sample of a full house because it is 3 of the similar kind, same kind, and these 2 are the pair are same kind. So you have to find out whenever you will have a 5 cards in your hand, what is the probability that it is a full house. How to do this problem? Very, very interesting problem, and just put some stress in your mind. Try to apply the basic principle of counting. How many ways you can do? See, first of all, that 5 card you can choose from a standard deck of 52 cards in how many ways? Yes, it's a 52 C 5 ways you can select. So this is the total number of outcomes. Now I have these 5 cards in my hand, and what is the probability that it will be a full house? For that I need to have that how many different ways the full house can be made. You have 13 different face value of the card, right? And in the first space you should have one face value. So try to get how many such possibilities are there. So I'll have 13 into, now I have 4 different suites of card. Among them 3 I have to select. How many ways you can do? Yes, it is 4C3. So out of this 13 different card, I have 13 choices, and these 13 choices, so it may be 1, it may be A, it may be 2, it may be 3, it may be 10, it may be J, it may be K, anything can happen among this 13. But I have 4 different suites, na? But I have to select 3 among them. How many ways you can select them? It's a 4C3 ways. So these first 3 card which are of same face value of different suites, you can get it in 13 into 4C3 ways. Next, you think that how many ways you can get these pairs. Now, once already one of your kind card is already selected, how many different kind of card is remaining? There are 12 different kind card is remaining because one is already selected here. So the second portion to fill it up, what is the total number of cases? It is 12 ways you have because one is already done in the first place. And you have to choose two from four different suites. How many ways you can do? It is into 4C2 ways. So the second portion you can fill it up with a 12 into 4C2 ways. And therefore, by basic principle of counting, I can have 13 into 4C3 into 12 into 4C2 way. You can select a like you can have this many different kind of full house. And therefore, what is the probability that I have a group of 5 cards? What is the probability that it will be a full house? It is this value 12 into 4C2 and divided by 52 C5, and you will get the answer. So the whole answer is, yeah, this is what we have discussed. The whole example is solved in a very formal way. It is the answer. And that's what we have discussed. 13 into 4C3 into 12 into 4C2. So therefore, this many number of full house are there. And how many total number of selection is possible? 52C5 ways. This value is this. Then the probability of that one full house is like getting a full house is this by this, which is a very small probability. I hope you understand that. So all the examples and contents are from these references. So if you like the video, if these videos are helpful for you, you may write the feedback in the comment box. Thank you very much.